Hi, welcome to our monthly webinar for the NCS 2030. This month we have Jassem Abbasi and Paul Anderson to talk with us, so I will let you take over. Thanks.
Yes, thank you, Lisa. Hello, everyone. I'm today going to have a talk about the physics-informed deep learning in general, and also introduce the applications that we found in our works and talk about the potentials for this very exciting approach, actually. So first, I will go with the introduction of physics-informed deep learning, inverse problems, and how it helps us in understanding the engineering problems and the scientific problems. And then I will talk about its applications, about the problem of imbibition, spontaneous imbibition in flowing porous media, two-phase flowing porous media, and the history matching of the experimental data, and the potentials of using these deep learning techniques for evaluation of incomplete or noisy data, and also talk about experimental verification and other cases. So let's at the beginning talk about this hype cycle of AI that today we all are hearing all day about AI and the newest changes. I don't know, ChatGPT and other generative AI techniques that's getting viral day by day and more popular day by day. But AI has a hype cycle that different AI techniques and AI topics have been clarified, that how it was evolved during time, and it will be evolved during the time. The scientific deep learning or physics-informed AI, you can see it to be at the beginning of its development, and it's just started growing, and in the next years you will hear much more about it. So it would be more and more exciting by passing the time in the next years. So before everything, let me just introduce the topic with this slide, this quote by Jensen Huang from NVIDIA, that all of the knowledge are led to physics equations, and now the physics equations are embedded into the neural networks, and it gives a gigantic opportunity for using physics-informed neural networks. So there are 4 pillars, like experiment, theory, simulation, and now data science is helping other pillars to move the science forward. For the data-driven approaches for scientific machine learning, we may use different approaches. So we may use lots of data, or have access to lots of data, or don't have any kind of data, or we have limited amount of data. Or we may have, we may don't use any physics in the deep learning approaches that we use, or use some physics or all physics in the calculation. So by physics-informed AI, we mean when we use some parts of data and some parts of physics, at least in our calculations, that it helps us to add more solidity in the calculations, and reduce the noises in the calculations, and makes the predictions more straightforward and more continuous in a way. So physics-informed neural networks, as a part of the physics-informed AI, is an approach that uses the concepts in machine learning, physics, and numerical methods at the same time, and merge them, combine them during the calculations, and by using like the optimization methods and optimizers, it will help us for solving the forward problems, history matching of the observation data, or inverse problems we call it, for the uncertainty quantification of our data or our system, and data-driven modeling of the problems that we are dealing with. Physics-informed neural networks are very reliable for mixed data, or we call it multi-fidelity data. They are very flexible to noisy or incomplete data. It gives us a quicker history matching opportunity, and they are more reliable for sensitivity analysis, and it gives us an opportunity for live interpretation of experiments or phenomena that we are investigating with very low supervision and checking. Inverse problems that are very interesting for us in this presentation are part of the scientific deep learning and scientific approaches that we use our observations, like experimental data or field data or any kind of data, for calculation of the inputs of our system or the characteristics or properties of the system that we are investigating. These problems are very challenging to solve normally because they are very imposed, meaning that there may be many solutions for the problem. They are super nonlinear generally, and usually we have very noisy data in the measurements and the observation data. So they are not very easy to solve using the traditional methods, and it would the complexity would be more and more with the increasing the complexity of the system. It has many applications in medical imaging, geophysics, like seismic interpretation, and many engineering problems. So physics-informed neural networks helps us to calculate the properties of the system as an inverse problem by merging the domain knowledge, or like our physical knowledge, PDEs of like flow in porous media in our case, or other information we have about the properties of the system, and also the data that we have from the observations. Data can be very noisy, can be very they can have different qualities, and they can be obtained from different sources like pressure, saturation, or any other kinds of data. And by mixing them, it can give us the properties of the system. Like here, we can calculate the U or radius of the system in this slide. As an example, I like to introduce a work from Caltech and NVIDIA that they use the scientific deep learning, or of course they didn't use pins for or physics-informed neural networks for these problems. They used the neural operators, but it shows the potentials of using physical AI for the problems. So here they use the neural operator to predict extreme weather conditions in different situations, and the results was very good. And also they were much quicker than the traditional approaches that you can see. It helps in having a twin model for predicting the weather in a way. So here is an example of the importance of using like neural operators here, or other scientific deep learning approaches that helps us in reaching to an ensemble of the prediction instead of having a single prediction or deterministic forecast. So here you can see the importance of having a deterministic having a deterministic forecast can lead to a high amount of error, but having a probabilistic forecast or ensemble-based forecast can help us in reaching a more safe and more reliable forecast about the future. Yes, so I quickly go to our problem. So a spontaneous inhibition problem that we are trying to interpret the experimental data that we may have. So the inhibition problem is a problem in laboratory of flow in porous media. So we have, it's a 1D problem normally when all of the faces in our core are blacked, except one of them that is exposed to the wetting phase. But the core is saturated with the non-wetting phase. After a while, like the non-wetting phase, like oil jumps out of the core and like water imbibes into the core. The problem is by nature maybe not very complex, but the equations are not also very easy to be solved because of different mathematical complications. So we apply the deep learning model that uses different types of deep learning approaches, like we use an encoder to encode our data. We use the Fourier transformation to capture the non-linearities in the model more easily. We use adaptive activation function to make the network more and more flexible for the complex and the non-linearities in the system. Then we use the automatic differentiation for calculation of the derivatives in the inputs versus in the outputs versus the inputs. So by defining this deep learning architecture and defining some collocation points versus time and a spatial variable like x, we could optimize or minimize our loss function to match at the same time with the physics of the problem, like the PDE of flow, and also the observation data that we have, like the recovery curve or in situ saturation data. Here you can see that we use the optimizer gradually reduces the loss term versus time, and also our error in the calculated parameters reduced versus time, and it leads to a plateau period that we can make sure that the final solution have been obtained. So you can see that the physics-informed neural networks, or PINs, could give a very, very accurate solution compared to the numerical simulators. We validated the calculation with IOR core sim simulator. And you can see that it could match also perfectly with the experimental data, for example, or the observation data here. And the results of the inverse calculations was very successful. You can see that we use an ensemble-based approach to capture the uncertainties in the calculations, and you can see that it could perfectly match with the experimental data or with the real data or the inverse parameter that we are looking for it with a very high accuracy, and all of the ensembles could lead to a good solution. This is the dynamics of converging to the true solution. You can see that it tries to match both the observation data here and the physics of the system. And by gradually reducing the errors, it leads to an accurate inverse parameter value that we are looking for. That is, here is a capillary diffusion curve. And here you can see that how defining a good input data for the deep learning models can impact the convergence of the deep learning model and leads to lower errors. Here you can see the loss landscape of different deep learning models when we use different inputs or input systems for the as the variables of the PDE. You can see that with increasing with decreasing the complexity of the inputs compared to the PDE or decreasing the complexity of the PDE that we are using, we will have more convex and more smooth loss landscapes that shows that how it can we can have quicker convergence and safer convergence to the true solutions. But one of the most important characteristics of inverse problems is that they are very ill-posed, as I mentioned before. So you may don't have one single solution for your observation data. Here, using an ensemble-based approach and random initialization of the inverse parameters, we could evaluate this, and we found that for the emission, spontaneous emission phenomena, when we have only recovery factor, we may have a unique CDC curve as the inverse parameter. But the inverse calculated REL-perm and PC curves are not unique. There may be infinite number of relative permeability or capillary pressure curves that match the experimental data. That this means that we should not rely on the calculations of the inverse parameters of the spontaneous emission for the REL-perm and PC. They are not necessarily true. So this shows the importance of using ensemble-based approaches to calculate the parameters of the system or history matching of the problem that we are investigating. It can be also applied. The problem can be applied for field scale observations as well, not only for the experiments. And also we evaluated how pins can help us in evaluating the uncertainties in the calculations during the test, for example, or when we have a limited amount of data or incomplete data. You can see that when we have a limited amount of data, there are many possible solutions for the CDC curves or for the inverse parameters that we are looking for it. And with increasing the amount of the data or the fraction of the data that we have from the test, the uncertainties in the system in the calculated parameters reduces. And this reduction in the uncertainty continues till we have some data at the finite acting period of the system. So it's so when the front of the flow touches the boundary at the end boundary of the core, we reached almost we reached to the infinite to the finite period. So if we have some data from that period, we can see that the errors in the calculations reduces significantly. So it's important that we know that which part of the from which part of the system or the test we have data or we don't have any data. Also, it helps us in evaluating the uncertainties in the calculations when we have noisy data, as you can see here, that there are with adding the noises in the system from top to the bottom, the uncertainties in the calculations increases. And this shows that how we should actually be careful about the calculations when we are using real experimental data that mainly they are noisy and they are uncertain. And how like a fraction of percent of noises can lead to a high amount of errors in the inverse calculations. So it's because that inverse parameters are very ill-posed normally. Also, as I mentioned, pins are very flexible for dealing with multi-fidelity data. By multi-fidelity data, I mean when we have data from different parameters, like we have data from pressure and saturation and recovery factor at the same time. So using like numerical methods to solve these problems are not very easy normally, but pins are very flexible for these kinds of data, and it without adding any computational load to the solver, it can easily capture any new types of data or new types of physics into the problem. And you can see here that, for example, with adding the pressure data only for 1 point or like 2 point, the errors in the predicted or the estimated capillary pressure curve reduced significantly. And also we can use the pins for when we have like different types of data, but we have some incomplete data. It helps us to reach to a final solution when we want to finish or terminate the experimental tests very sooner. So here you can see that with only having 50% of the experimental data recovery factor and just one snapshot of the distribution of saturations in the core, it helped us in reaching to a very accurate predictions or estimations of the CDC curves. And by using these techniques, we may able to reduce the experimental test from like 2 orders of magnitude. That makes the costs and makes many brings many advantages in the calculations and saves many costs of the experiments and also times of the developments or experimentation. We use this technique also to history match and calculate the parameters of a real experimental data. We had data from Root et al. So they had some data about the recovery factor, the pressures versus time at some point, and also the local saturation versus time at different positions of the core. So we try to use all of this data at the same time, very simply using pins, and calculate the parameters of the system. That could be like the RelPerm and PC and other parameters like CDC curves. You can see that the pins could almost with a high quality and high accuracy match the experimental data as much as it was possible, the recovery and pressure data, but the data was not very complete and it was very noisy. We found it, and it added some complexity in the calculations. Well, that the reference calculations that published with the main paper was not very accurate. We found it, and there were many opportunities to improve the calculations. And you can here see that with changing, with repeating the calculations using an ensemble-based approach, we may calculate different RelPerm and PC curves and even the CDC curves. This shows that how the real having noises in the data or dealing with real case data may bring many uncertainties in the calculations, and it's important to consider that and go through the ensemble calculations, not deterministic calculations for the calculation for the history matching and like field development and other projects that we may have. And you can see that here adding more data in the synthetic case helped in reducing the noises in the noises in the inverse calculated parameters, but adding the data in the experimental case added more noise in the calculations. It shows that dealing with different types of data added noise to the system, and it shows us the real uncertainty of the system. It's important to use our data sets or all of the data that we have from the system, from like the field or from the experiments at the same time during the calculations, because there may be lots of uncertainty in the system that we don't capture it if we don't consider all of the data that we have. But that's not very easy using traditional numerical methods. So it was just beginning of our study in a way, and we are continuing with more complex cases like with flow in fractured porous media, and having access to more accurate data sets, more larger data sets of the flow in porous media like in situ saturations. And we want to try to use pins for these cases because simulating these cases using numerical methods, even like CFT solvers, is not very easy at all. But if also you want to use this data for inverse calculation or for history matching of the parameters, it would be a nightmare, I believe. So we are at the moment working on this project, and hopefully in the next months we will come up with some reports on these projects as well. Yes, thank you for your attention.
Great, thank you so much. Very interesting presentation. Does anyone have any questions? No.
Maybe I can ask some questions.
Yes, sure.
So with the introduction of PIN, what do you consider to have been the greatest advances compared to traditional machine learning?
Yes, so I think pins can help us in problems that we don't have enough data. So we have so in the scientific problems we may have that problem. In many cases we have those kinds of problems that we don't have access to enough amount of data. So it's not possible to train our neural networks only based on data, because that neural network wouldn't be reliable. And also there are many advantages. There are super advantages for the inverse problems as we focus in this study, because the computational time for forward problem and inverse problems in pins is almost similar. So you don't need the extra amount of iterations over your calculations to perform inverse calculations or history matching. So it's really advantageous if you can use it for your inverse calculations. You will have a quick solution for your cases in that problems, I believe.
And the major bottlenecks now regarding PIN, what do you consider that is?
Yes, I believe reaching the true solutions of the PDE is still a challenge. So it's still the PIN models are not very powerful in reaching the true solutions, and this complexity increases with the time. But you know, it's a very new method, and like for example this numerical methods like for finite element methods. So now we have about 50 years finite element methods in the market, and they are very mature, but pins are still in their childhood, so they are growing very fast to fix that problems, and newer approaches are coming in the literature. But yeah, they are still not very powerful in capturing the complexities in the system sometimes.
Thank you for the great presentation.
Thank you, Paul.